Hi everyone, welcome to another video by Cheenta and I'm Rajdeep. Today is, in my understanding, the final video in our ongoing number theory series. It has faced some pauses and some delays, but as promised, I will today discuss the Legendre symbol and quadratic reciprocity. Quadratic reciprocity is in many ways the crowning achievement of, let's say, 18th to 19th century mathematics. It was Gauss's favorite theorem. He truly loved it. It's a beautiful result and it often gets lost in Olympiad trickery. I will talk a little bit about the meaning of it and what it represents. There won't be any particular illustrative problem today. There's simply going to be the math, which I think is a good note to end the series on. And I hope you enjoyed. So let's get into it. Right, so I guess the best place to start is where I promised, which is Diophantine equations. So at this point, I have sort of spoken about linear Diophantine equations, how to solve them, how to think of them. So in general, if someone gave you a setup like this, ax plus by is equal to c, you could analyze it mod p, and you could get a relation in between x and y mod p, and that would give you some information. Sometimes that's enough information to solve the problem, sometimes it's not. Sometimes you have to test a few different terms. You can combine the information of different moduli using the Chinese remainder theorem, which is all discussed in previous videos. Today I want to talk about the next step, since linear is out of the way, quadratic. So ax square plus let's say bx plus well, technically the most general quadratic form is this, plus dx plus ey plus f. This is the most general quadratic form, but you can do substitutions which are rational and you can get them into a form which is simpler, which is just this. So in particular, you can get rid of the cross term xy by making a smart substitution. In particular, you'll group together the x and y. So this comes after a variable change, but you can do this. And so in particular, how do you solve this kind of a thing? This is a 2-degree Diophantine, and obviously you know how to do some, you are aware of some of these. So a 3-variable example, very famous one, is this, right? There's a Pythagorean equation. We know the integer solutions to this, and if you don't, I definitely advise you to check it out. Primitive Pythagorean triples, how do we find them? There's a lot of beautiful theory behind that. But generally, how would you approach something like that? So for ease of conversation, let me start with a single variable quadratic. Ax square plus bx plus c is equal to 0. There's many ways of approaching this. Sometimes it's very simple to solve things like this, sometimes it's not. And a lot of the times you don't have a single variable, you have a 2-variable thing. But regardless, let's pretend this is what we have now. How do you analyze this mod p? Prime. You can, so the general strategy that I would want to take is, let me get a nicer form, let me break this into, let me complete the square, right? So after completing the square, I'll get something like, it's kind of a big thing, but I'll get a square is equal to some number, some k, let's say mod p. And this is a linear thing. This is some, let's say some capital AX plus capital B square is equal to k mod p, where if everything goes well, I can clear denominators and all. Maybe I won't have to, but regardless, you can get it into a form like this. Now what do you do? This ax plus b you can deal with. So at this point, you can even consider it to be a different variable, capital X square. So solving a quadratic mod p comes down to solving this kind of a basic quadratic. And there's a whole thing which I will skip, which is like mod p will only tell you so much information. How do you solve the full thing? And there are some very beautiful results in some advanced number theory which says that if you can solve a quadratic form, and so the most general thing I just wrote down into 3 or however many variables, you can solve that thing. There are solutions, integer solutions to that kind of an equation modulo all primes or even all but finitely many primes. Then there's a solution over the integers. It's called the Hassa principle. It's extremely fancy and there's no way I can get to a proof of it. It's a very beautiful piece of math though. So in a way, this is not even a futile thing. If you could somehow magically solve this quadratic modulo all primes, you're good. So it does give you a recipe of sorts of solving quadratics, perhaps not the most nice one, but regardless, this is what it would come down to. Now, how do you answer this question? This is what brings us to the Legendre symbol. Or rather, before the Legendre symbol, the notion of a quadratic residue. That hyphen is not required. A quadratic residue. What is a quadratic residue? It's a residue which is the square of something. So it's exactly this actually. K is called a quadratic residue mod P, QR in short, QR mod P, if there is such an X, if there is a solution to this. So a quadratic residue is just something which is the square of another residue. So let's take an example, let's go mod 5. What are the square residues mod 5? So that might seem like a weird question. Not all residues can occur as a square. So look at what you do get. If you square 0, you get 0. If you square 1, you get 1. If you square 2, you get 4. If you square 3, I don't need to do anything because 3 is it's minus 2. So squaring it actually gives me the same thing as 2. But 3 square is 9 and 9 mod 5 is 4 again. And 4 square is 16, which is 1. So these are all. So this is all the possibilities of squares mod 5. So in particular, 3 is not a QR. So we write that as NQR. Non-quadratic residue, NQR mod 5. In particular, this gives you like a quick solve to something like, let's say x square plus, let's say 3 is equal to 5y cube, right? At the outset, how do you solve something like this? This is a hard problem. How do you do this? So in that, the question is solve this over the integers. But if you went mod 5, you would get that, I misspoke, x square minus 3. But even then it actually works out. Let's say x square plus 3 for the sake of completeness. So 3 is not a quadratic residue and neither is 2. 0, 1 and 4 are. So in particular, if I look at this equation mod 5, I get that x square is common to minus 3 or 2 mod 5 because this term dies, right, when I go mod 5. So if there was a solution to this equation, it would have to satisfy this thing mod 5. But this has no solutions because there's no thing that you can square to get a number which is 2 mod 5. No square number leaves a remainder of 2 when divided by 5. That's kind of remarkable to even think about. It's very simple, it's extremely basic, but it's interesting that we can do this kind of math, that we can make these far-reaching statements. Because if you were going through a list of squares and you would just notice this curious pattern that, oh wow, it just seems like any number which is a square, so like 1, 4, 9, 16, so on, all of these seem to follow some sort of a rule, and I look at them, when I look at their remainders mod 5. There's a very basic explanation in this case. And it also lets you solve equations like this very quickly, very easily. So that's the idea, and that's the idea with quadratic, that's what a quadratic residue is. You can ask some very basic questions. How many quadratic residues are there mod P? And sort of that will also answer the question of how many non-quadratic residues are. If something is not a quadratic residue, it's a non-quadratic residue. Are there mod P? In this case also the answer is pretty simple. You just have 1 square, 2 square. You just square all the numbers and you ask how many of these are distinct. So in particular, you ask the question, when can two different squares, in that the squares of two different numbers, be the same mod P? But that can only happen if P divides x square minus y square. That's what it means actually for two numbers to be congruent mod P. But P divides, this implies P divides x minus y and x plus y. It's a simple check that both of these, this implies that either P divides x minus y or P divides x plus y. Which is the same thing as saying that either x is minus y or plus y mod P. So either x is the same thing as y mod P, so x and y are the same residue, or x is minus of it, which is pretty obvious actually if you think about it. You square the negative of a number, you get the same thing. But this concretely answers the question, when can two different squares be the same mod P? And so this tells me that if I just take 1 square, 2 square, all the way up to P minus 1 by 2 square, where P is an odd prime. With 2 is always going to be a sore thumb in these kinds of things. P is odd whenever whenever it's not mentioned. And these are all distinct because nothing here is the negative of anything here. And so there are p minus 1 by 2 quadratic residues, not considering 0. This is simply a matter of convention. Like, are you going to consider 0 to be a quadratic residue? I mean, technically it is, but we usually only talk about like the non-zero residues. So 0 is a square mod p, but that's very easy to see. That's why we restrict to. And so this also implies that there are p minus 1 by 2 non-quadratic residues, right? P minus 1 minus p minus 1 by 2. Good. So the how is answered. Now, can I find some sort of a relation? So in particular, it's obvious that if I multiply a quadratic residue with a quadratic residue, I'm going to get a quadratic residue. A quadratic residue is the square of something, right? Some k square. This is some L square. When I multiply them, it's k square. So that part's easy. That leaves two harder questions to answer. When I multiply a QR with an NQR, what do I get? Not hard to see that this has to be a non-quadratic residue, because if it was a quadratic residue, and since I'm working with non-zero entries, I can invert. So in particular, if a QR times an NQR was a QR, right? If a square times a non-square was a square, I could take this guy to the other side, right? And the inverse of a square is also going to be a square. That again, if you remember what I taught about inverses, this should not be surprising at all. If x square is equal to k, then 1 by k, right? K, the inverse of k mod p, is just 1 by x square. This might be weird to look at when we are working mod p, but I've already justified that fractions, when you're working with non-zero things, mod p for a prime, completely justified. So in particular, if a quadratic residue times a non-quadratic residue, then I could take this quadratic residue onto this side, and it would give me that NQR is equal to QR into QR. Can't happen. Which leaves up the final question of what happens when I multiply two non-quadratic residues. This is the most fun thing, and it turns out that it's a quadratic residue. There's a very clever argument for this, which I'm tempted to leave as homework, if you will. I'll give you a hint. You have the list of numbers from 1 to p minus 1. Half of these are non-quadratic residues, half of these are quadratic residues. Multiply every number here with a non-quadratic residue. See what happens. So I'll leave the proof. It's a very nice result. I'll leave this as homework. Pause the video and try it. It's pretty simple. But this gives an interesting picture. This is a QR times a QR. So it's a QR. QR into NQR is NQR, NQR into NQR is QR. This is very plus minus 1, right? So QR behaves like 1 and NQR behaves like minus 1. And so that's the vibe that you get, plus minus. So this motivates the definition of the Legendre symbol, which is just like a condensation of what we've done till now. This is called the Legendre symbol. You can call it whatever you want. If you were in a rush, you would say A by P, but just you could also say A Legendre P, whatever you want to call it. This is defined as 1 if A is a quadratic residue mod P. Recall that we don't consider 0 to be a quadratic residue for no reason other than convention, and because you get these nice symmetry between QRs and NQRs in terms of quantity. That symmetry gets broken if you include 0. So it's just for like aesthetics that we don't include 0. It's 0 if A is 0 mod P, right? We don't want to mess with 0. And it's minus 1 if A is NQR. What we've just proven is the multiplicativity of we've proven the multiplicativity of the Legendre symbol, by which I mean A by P times B by P is straight up equal to AB by P, where A and B are integers. Integers, P is a prime. We've just shown this, right? If A and B are both squares mod P, non-zero, then we've shown that it's a square, and so in that the product of A and B is a square. So if these are both 1, then this is going to be 1, checks. If one of A or B is not a square and the other is a square, then the product is not a square. 1 into minus 1 is minus 1. And finally, the one I left out but can be done with some effort, -1 into -1. Both are non-quadratic residues. It's 1. This is very pretty. Like, admittedly, it's very, very pretty. Super nice. And this also makes a by thing into what's called a character, and it leads to some very beautiful theory on that end as well. If you explore that relation further, it gives like a homomorphism or whatever. It's a structure preserving map in that this thing of, so the map where A goes to A by P is a structure preserving map. It preserves multiplication. And so when you explore that relation further, you get some beautiful theory with Ghosh sums, and it also leads to a proof of quadratic reciprocity, which we'll see later. Right, so that's that. And so at this point, we also would like to get a more explicit, like how would I calculate in general when A is a quadratic residue mod P, right? This is because it's a hard question in general, is why quadratic reciprocity is so revered. So first I'll give you a simple answer and then I'll delve a little bit deeper. So the simple answer is you have something known as Euler criterion, which is this. It's known as the Euler's criterion, which there are many of at this point. There's so many Euler's criterion. It's not worth it to keep track of all of them. It's fine. You just know the result. This weird result is much harder to remember than just thinking about primitive roots, which we have covered in my last video in the number theory series. Recall that all the non-zero residues mod P are powers, different powers of some G, where G is a primitive root, which exists. So I made that claim. I did not prove it because it's a hard proof, and I asked you to look it up, and I hope you did. G is a primitive root mod P. Then G generates the group of residues. So the powers of G, when I look at them from 1 to P minus 1, is all the residues, non-zero residues, mod P. 1 to P minus 1 in some order. This already gives you a very easy way to test for what residues are squares and what are not. Think about it. G square is obviously a square, right? Whatever it is, like mod P, mod 7, for example, 2 is a primitive root. I think. I could be wrong, but I do think 2 is a primitive root. So 4 is obviously a square. G square is obviously a square. G to the 4 also obviously a square. It's the square of G square. Right? So 2 to the 4 is 16, which is 9 mod 7, a square, right? 3 square. So generally, G to the 2k is going to be a square, is a QR mod P. But also, if you had a G to the 2k plus 1, this is not a quadratic residue mod P. How could it? If it was the square of something, it would have to. So because everything is a power of G, if it was the square of something, it would be an even power, right? So this gives a very easy visibility test. If you had a whole of a primitive root and you could calculate all of its powers, for like a small prime, like 13 or something, it would give you very quickly what the primitive roots are. And it also justifies this result very easily. G to the k to the power P minus 1 by 2 is 1 if k is even, right? If k is even, you just get up. So if k is even, some G to the 2 L, let's say, to the power P minus 1 by 2. What is that? G to the P minus 1 whole to the power something. But that's 1, obviously. If you have an even power, it cancels with the 2 and only leaves a P minus 1. But G to the P minus 1 is obviously 1. Anything to the P minus 1 is 1. As long as you don't have a 0 thing. If G is not a square, then you have something which when you square, you get, right, G to the P minus 1 by 2. When you square it, you get 1, right? Because that's G to the P minus 1. We just saw that this can only happen if it's 1 or minus 1. So if it's not 1, it's minus 1. And so primitive roots give a very simple proof of Euler's criterion. So this gives us our first result, which is this. Is congruent to minus 1 to the power P minus 1 by 2. We already covered this. What is this saying? This is saying that minus 1 is a square mod P if and only if P minus 1 by 2 is even, right? If it's even, then you have minus 1 to an even number, which is 1. So minus 1 Legendre P is 1 mod P. but minus 1 Legendre P is either 1 or minus 1. So if it's congruent to 1 mod P, it's equal to 1, and so on in the odd case. P minus 1 by 2 is even is the same thing as saying 4 divides P minus 1. We already covered this. So we get a nice, very beautiful interpretation of this. There is another result which is harder significantly, which is saying when is 2 is a quadratic residue. So we have a formula. So you do already have a formula, which is 2 to the power P minus 1 by 2. Unfortunately hard, right? It doesn't immediately tell you what it is. If I give you a really large prime, you have no way to know, because you have a really large power of 2. You'll sit and calculate that, and then you'll reduce it mod P. It's a lot of work. If you have a really large prime, it'll take you a long time. This is not so satisfactory. You have a much more satisfactory result, which is minus 1 to the power P square minus 1 mod by 8 mod P. This is equivalent to saying that 2 is a square mod P when either P is congruent to 1 or minus 1 mod 8. You can see that that's what it translates to. So 1 or 7 mod 8. Think about, okay, so now that we've covered the simpler results, I want you to think about what the framework here is. We ask a quadratic question. When is 2 a square mod P? When is minus 1 a square mod P? And what we get are linear results, linear congruences. Like that in itself should be very surprising. Minus 1 is a square mod P when P satisfies some basic linear congruences. It's 1 mod 4. Yeah? You have a square condition translating to a condition on P, which is also a linear congruence. That's crazy. Like, to me, that's such a crazy result. And similarly, 2 is a square mod P if P is either 1 or 7 mod 8. That's a linear congruence. It's also very explicit. Like, it's very easy to check whether P is a 1 or 7 mod 8. It's a very simple check. It's very quick. Much quicker than seeing what this is mod P, right? That's why these results are so powerful. So without further ado, quadratic reciprocity. I'll just write it down and I'll interpret it later. P by Q. Well, see, I just did that. It's not P by Q, it's the Legendre symbol of P over Q. QP is equal to minus 1 to the P minus 1 by 2 times Q minus 1 by 2. So pause the video and stare at it for a, but let me say this first. P and Q are odd primes. So this does not work in P is 2, but we already covered what happens when P is 2. And that minus 1 is way more helpful than you realize, because you get results like when is minus 2 a square mod P. That can be very helpful. I'll get to why, but it's because of multiplicativity, you get this, right? So either both minus 1 and 2 are not quadratic residues, or both are quadratic residues. And you have a basic check, right? A mod 8 check actually, right? P congruent to 1 mod 4 implies P is either 1 mod 8 or 5 mod 8. So you have some basic checks that you can, it's a very simple result then. Right, so quadratic reciprocity says this. P is a square mod Q. When is P, this is asking the question, when is P a square mod Q? This is asking, rather answering, both are answering the question, when is Q a square mod P? And turns out those questions are essentially the same. They are just correlated by this simple factor. They're either like, so you can check the cases. This is saying if either of P or Q, so if P or Q, so this is a corollary if you will, is 1 mod 4, what does that mean? That one of these numbers is even, and so you have an even power of minus 1, so it's 1. If P or Q is 1 mod 4, then P is a square mod Q only if and only if Q is a square mod P. Okay, I'll show you the implication right away. Take a small prime P and a large prime Q. 3. This is saying that if Q was 1 mod 4, 3 is not 1 mod 4, so say Q is 1 mod 4, then 3 is a square mod Q only if Q is a square mod 3. Take some massive prime, right? Like, let me look up right now a large prime mod 1 mod 4. So, I have just seen that 4001 is a prime, and it's obviously 1 mod 4. This is saying that 3 is a quadratic residue mod 4001 if 4001 is a quadratic residue mod 3. One of these is significantly easier to answer than the other. What are the squares mod 3? 0 or 1? Clearly, you can't get 0 mod 3 because you're working with primes. It's 1, whether or not it's 1 mod 3. Is 4001 1 mod 3? It's not. So I think for the sum of the digits is 5. It's minus 1 mod 3. 4001 is 4098 is, I think, no, 4099, whatever. So yeah, 4001 plus 1 is 1 mod 3, so it's minus 1 mod 3. So it's not a square, which means this is minus 1. So 3 is also not a square mod 4001. Imagine, so going through the possibilities, you have to check every number from 1 to 2000, square them all, and see whether any of these numbers are 3 mod. Like when you reduce them modulo 4001, you get 3. But you get an immediate answer in this case. It's not. It has saved you an insane amount of calculation. And also, in the same vein as the result I was saying, using multiplicativity, you can generally answer this question. What is this? Just break it into its prime powers. Say, p1 to the power k1, let's say t to the power kt, p by multiplicativity. Also, if it's a square, like a square is always a square mod p. Like I don't have to ask, is 4 a square mod p? 4 is a square mod any p because 4 is a square. So I can ignore the square parts and it leaves me only with all the odd exponent primes that show up in A. So some product of primes. Okay. Just remember multiplicativity is this. So quadratic reciprocity is actually the final thing you need. And so there might be a 2 here as well, but we know how to deal with that. Is the final step you need to always answer this question. And what is the answer you're getting? It's an answer, so all of these, so when is P1 a square mod P? When, depending on what, these are modulo 4, these are basic congruences. Think about what this is saying. If P is small, as it was in this case, these are just linear congruences again. So P is a square, so let one of them be fixed and the other be variable. That's what I'm trying to say. Fix P and let Q vary. So fix P and you have some variable prime x. Then P is a square mod x plus minus depending on the power of, depending on what x is mod 4. So let's for now let x only be 1 mod 4. If it was 3 mod 4, there will be a minus sign, that's all. So if x was 1 mod 4, then P is a quadratic residue mod x only if x is one of the finitely many square moduli mod P. Finitely many checks. So some A1, A2, AK mod P. These are linear congruences. So the big package of quadratic reciprocity, if I include the result for 2 and minus 1, is this. That the answer to whether A is a square mod P is just a bunch of linear congruences, right? Even with this multiplicativity thing, you just get a bunch of linear congruences modulo P1, P2 up to Pt. By Chinese remainder theorem, you can merge them into just finitely many linear congruences. So you can always answer the question, is A a square mod P, by just checking finitely many linear congruences. This is a beautiful result in my eyes. And it's also a result that fails to hold once you start asking other questions. So there are results. There's cubic reciprocity, there's quartic reciprocity, there's higher reciprocities which can all merge into one of the crowning achievements of mathematics in the 20th century, which is called class field theory. Extremely fancy math, which even I'm not fully aware of, called art and reciprocity. But this is a beautiful result which in some sense there's a case called the non-abelian case. So the proof of reciprocity is even more beautiful if viewed in the right context. It's about the splitting of primes in cyclotomic fields, whatever that means. Once you generalize that from cyclotomic fields, which are abelian, to non-abelian cases, whatever that means, you don't get these beautiful results. You don't get simple linear congruences. You need more information. You need sometimes some calculus-based information. So that what you get here is a gift. And I hope that I've convinced you of that in this very long video. If you have watched it till the end, thank you very much for giving me so much of your attention. I hope you enjoyed it. I did not give you an example problem here because I wanted to convey a larger idea than just one problem. But I have given you the tools. Whenever you want to solve some sort of a square thing, you get any quadratic equation, x square, as I said, x square plus 3x plus 5 is equal to 4x square plus 7. You can choose the right moduli, and it sometimes comes down to is some numbers, 27, a square mod 5, right? You know how to deal with them now as well. Apart from knowing this beautiful result, you also know how to deal with them. I did not give you a proof of quadratic reciprocity because it's far too long and far too convoluted. Do look it up and don't be discouraged if you don't fully get it. There's a lot of time to learn math and lots of places to learn it from. As I said, the most natural and the most beautiful proof is the one that you get through splitting phenomena in cyclotomic fields, which is a bit fancy, but there are other proofs. So regardless, I hope you enjoyed the video. Thank you so much for watching. Bye bye.